September 11th, 2019. The Hubble Space Telescope Operations Center, Baltimore. Dr. Björn Benneker can't believe what he's seeing. The spectral data from K2-18B, a planet 124 light-years away, shows something that shouldn't be there. Not just water vapor, which would be remarkable enough, but alongside the water signature there's something else. Something that makes his hands shake as he rechecks the calculations for the 5th time. Dimethyl sulfide, DMS. On Earth, there's only one source of DMS in the atmosphere: life. Specifically, marine phytoplankton. It's a biosignature so reliable that finding it in an exoplanet's atmosphere would be considered a smoking gun for biological activity. But K2-18b isn't Earth. It's a world unlike anything in our solar system. 8 times Earth's mass, 2.6 times its radius, orbiting a red dwarf star every 33 days. It's what astronomers call a sub-Neptune, or mini-Neptune. We don't have anything like it orbiting our Sun, yet there it is, possibly harbouring the first detected sign of life beyond Earth. Benneker calls his colleague, Dr. Angelos Tsiaras at University College London. Tsiaras has been analysing the same target with different instruments. "Are you seeing what I'm seeing?" Benneker asks. There's a long pause, then Tsiaras responds, "The water is definite. The DMS, we need more data, but if this is real..." He doesn't finish the sentence. He doesn't need to. If the DMS signal is real, they're looking at the most important discovery in human history. Evidence of life on a type of planet that might be the most common in the universe. Because here's what makes K2-18b special. It's not special at all. Sub-Neptunes like K2-18b are everywhere. They're the most abundant type of planet in the galaxy. If K2-18b has life, it means life doesn't need an Earth-like planet. It means the universe might be absolutely teeming with biology on worlds we never imagined could be habitable. The James Webb Space Telescope would later scrutinize K2-18b with unprecedented precision, searching for confirmation. What it found would challenge everything we thought we knew about where and how life could exist. K2-18b wasn't just another exoplanet. It might be the blueprint, the template showing us what most habitable worlds in the universe actually look like. Not Earth-like at all, something far stranger, and possibly far more common. To understand why K2-18b is revolutionary, you first need to understand what we expected to find when we started discovering exoplanets. For decades, astronomers assumed other solar systems would look like ours. Small, rocky planets close to the star, gas giants farther out, everything orbiting in neat, nearly circular orbits. We were completely wrong. When we started finding exoplanets in the 1990s, nothing looked familiar. Hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our Sun. Super-Earths, rocky worlds larger than Earth but smaller than Neptune. Planets on wildly elliptical orbits. Planets orbiting binary stars. Rogue planets wandering between stars with no sun at all. But the biggest surprise was what we found most often. Worlds between Earth and Neptune in size, something our solar system completely lacks. These sub-Neptunes or super-Earths, depending on their composition, make up about 30 to 50% of all planets. They're the universe's favourite type of world, and we have no idea what they're really like because we don't have one to study up close. K2-18b sits right in the middle of this mysterious category. With 8 times Earth's mass and 2.6 times its radius, it's too big to be a rocky super-Earth, but too small to be a proper gas giant. For years, scientists assumed such worlds must be inhospitable. Mini versions of Neptune with thick hydrogen-helium atmospheres, crushing pressures, and no solid surface. But K2-18b broke the mold. First came the 2019 discovery of water vapor in its atmosphere, the first such detection for a planet in the habitable zone of its star. The habitable zone is that Goldilocks distance where liquid water could exist on a planet's surface, not too hot, not too cold. K2-18b orbits its red dwarf star right in the middle of this zone. Dr. Niku Madhusudan at Cambridge University immediately realised something profound. Everyone was thinking about Earth-like planets as the places to look for life. But what if we've been thinking too small? What if these sub-Neptunes, which we've been ignoring, are actually the sweet spot for habitability? Madhusudan's team ran atmospheric models of K2-18b, and what they found was stunning. Instead of a mini Neptune with a thick gas envelope and no surface, K2-18b might be something completely different. A Hycean world, a portmanteau of hydrogen and ocean. Picture this, a planet covered entirely by ocean, tens or hundreds of kilometers deep. Above the ocean, a hydrogen-rich atmosphere much thinner than Neptune's but thicker than Earth's, creating a massive greenhouse effect. The atmospheric pressure at the ocean surface would be similar to Earth's deep ocean trenches, extreme but not impossible for life. The temperature could range from just below freezing to 200 degrees Celsius, 392 degrees Fahrenheit, depending on location. Hot, but within the range of Earth's extremophiles. It's like nothing in our solar system, Madhusudan explains. But when you run the numbers, when you model the chemistry and physics, it works. These Hycean worlds could be habitable, and they're everywhere. The implications hit the astronomical community like a thunderbolt. We'd been looking for Earth 2.0, assuming life needed a rocky world with a thin atmosphere. But what if life's requirements were far more flexible? What if the most common habitable worlds were these water-wrapped, hydrogen-shrouded planets we'd been dismissing? Dr. Sarah Seeger at MIT, who has spent her career modelling exoplanet atmospheres, puts it in perspective. If Hycean worlds are habitable, the number of potentially life-bearing planets in our galaxy doesn't just double or triple, it might increase by a factor of 10 or more. We're talking billions of worlds. But could life really exist in such an alien environment? The answer might be stranger than we imagined. Every living thing on Earth, from bacteria to blue whales, is built from the same chemical toolkit: carbon-based molecules, liquid water as a solvent, DNA and RNA for information storage, proteins for structure and function. It's tempting to think this is the only way life can work, but K2-18b forces us to think bigger. The hydrogen-rich atmosphere of K2-18b creates chemistry impossible on Earth. Hydrogen is the universe's most abundant element, but on Earth, our oxygen-rich atmosphere makes free hydrogen unstable. It quickly combines with oxygen to form water. But on a world like K2-18b, hydrogen dominates, and hydrogen chemistry is weird. Dr. William Baines at MIT has spent years working out the biochemistry possible in hydrogen-rich atmospheres. It's not just different, it's richer, he says. Hydrogen allows for chemical reactions that are impossible in our oxidizing atmosphere. You could have metabolisms based on methane and ammonia. You could have organic molecules that would instantly decompose on Earth, but are stable there. Consider photosynthesis. On Earth, plants split water molecules and release oxygen. But on K2-18b, organisms might split methane or ammonia instead. The waste product wouldn't be oxygen, but hydrogen or nitrogen. The entire ecological cycle would be alien to us. The pressure changes everything too. At the surface of K2-18b's ocean, the pressure might be 100 times Earth's sea level, similar to our deep ocean. But pressure isn't just about crushing things. It changes chemistry fundamentally. Molecules that can't form at low pressure become stable. Proteins fold differently. Cell membranes behave differently. Dr. Avi Loeb at Harvard has modelled possible life in high-pressure, hydrogen-rich oceans. You might have organisms with metallic hydrogen in their cells, something that only exists at extreme pressures. Their biochemistry could involve superconducting proteins. They might generate energy through quantum processes we haven't imagined. But the most intriguing possibility came from that controversial detection of dimethyl sulfide, DMS, in K2-18b's atmosphere. On Earth, DMS is only produced by life, specifically by marine microorganisms. It's part of the global sulfur cycle, helping to form clouds and regulate climate. Finding DMS on K2-18b would mean one of two things. Either there's a non-biological process producing it that we don't know about, or there's life. And not just any life. Life sophisticated enough to alter the planet's atmospheric chemistry on a global scale. Dr. Clara Souza Silva at the Center for Astrophysics has spent years cataloguing biosignatures, chemicals that might indicate life. DMS is as close to a smoking gun as we get, she says. There's no known abiotic process that produces it in significant quantities. If it's really there, it's huge. But confirming the DMS detection has proven frustratingly difficult. The signal is at the edge of detectability, confused by overlapping spectral lines from other molecules. We need more sensitive instruments, longer observations, different wavelengths. This is where the James Webb Space Telescope entered the picture. With its massive mirror and advanced spectrographs, JWST could analyse K2-18b's atmosphere in unprecedented detail. The observations, conducted through 2023 and 2024, revealed not just the presence of water and methane, but a whole suite of molecules that paint a picture of a chemically dynamic world. The results were complex. The DMS signal remained ambiguous, present in some analyses, absent in others. But other discoveries were just as intriguing. Methane and carbon dioxide in proportions that are difficult to explain without biology. Possible phosphine, another potential biosignature. Evidence of photochemical hazes that could be biological in origin. Disequilibrium chemistry suggesting active processes refreshing the atmosphere. Dr. Caitlin Rasmussen at the University of Washington studies atmospheric disequilibrium as a biosignature. Life creates chemical imbalance, she explains. On Earth, having oxygen and methane together is impossible without life constantly producing both. K2-18B shows similar impossible combinations, chemicals that shouldn't coexist, but do. But there's a catch. We don't fully understand the atmospheric chemistry of sub-Neptunes. What seems like biological disequilibrium might be natural processes we haven't encountered. K2-18B might be teaching us new chemistry, rather than showing us alien biochemistry. The term Hycean, hydrogen plus ocean, was coined by Niku Madhusudan in 2021, but the concept has revolutionized how we think about habitability. These worlds represent a completely different mode of planetary existence, one that might be far more common than Earth-like planets. Here's the basic structure of a Hycean world. Start with a rocky or icy core a few times Earth's mass. Add a global ocean hundreds of kilometers deep, far deeper than Earth's oceans. Top it with a hydrogen-dominated atmosphere, thick enough to create a strong greenhouse effect, but thin enough to avoid crushing pressure at the ocean surface. The result is a world that could maintain liquid water across a huge range of distances from its star. But Hycean worlds come in varieties, each with its own potential for life. Hot Hyceans, close to their stars, with surface temperatures up to 200 degrees Celsius. On Earth, we find life at these temperatures around deep-sea volcanic vents. The upper atmosphere might be cooler, with distinct temperature layers creating multiple potential habitable zones. Cold Hyceans, far from their stars, with surface temperatures below freezing. But the thick hydrogen atmosphere creates such a strong greenhouse effect that the ocean remains liquid beneath an ice shell, like Europa or Enceladus, but far larger. Dark Hyceans, tidally locked to their stars, with one side in permanent day, the other in permanent night. The night side might be more habitable, protected from stellar radiation, while still warm enough for liquid water. Thin Hyceans, with minimal hydrogen atmospheres, more like supersized versions of Earth with global oceans. These might be Hycean worlds that have lost most of their hydrogen over billions of years. K2-18B appears to be a temperate Hycean, right in the middle of these extremes. Its temperature could range from 0 degrees Celsius to 40 degrees Celsius at the ocean surface, perfectly compatible with life as we know it. But the conditions below the surface might be even more interesting. Dr. Amit Levi at Florida Tech has modelled the ocean structure of Hycean worlds. You don't just have an ocean, you have layers. Different pressures create different phases of water. You might have normal liquid water at the top, then high-pressure ice layers, then a second liquid ocean above the rocky core. Each layer could have its own ecosystem. These high-pressure ice layers, Ice 6, Ice 7, and exotic forms that don't exist on Earth, aren't the frozen water we're familiar with. They're hot, dense, and could transport nutrients between ocean layers. They might even be habitable themselves, with life existing within the crystal structure of high-pressure ice. The energy sources for life on a Hycean world would be diverse. Stellar radiation. Even through the thick atmosphere, some light reaches the ocean surface. Photosynthesis might work, though perhaps using infrared light from the red dwarf star. Chemical energy. The mixing of different water layers, each with different chemistry, could drive metabolisms, like Earth's deep-sea vents but on a global scale. Tidal heating. If the planet has moons or is tidally stressed by its star, internal heat could drive volcanism on the ocean floor, creating chemical oases for life. Atmospheric electricity. The thick, turbulent atmosphere might generate massive lightning storms, creating organic molecules and providing energy for aerial ecosystems. But perhaps the most exciting aspect of Hycean worlds is their longevity. Earth's habitability is temporary. In a billion years, the sun's increasing brightness will trigger a runaway greenhouse effect. But Hycean worlds could remain habitable for tens of billions of years. Red dwarf stars, which most Hyceans orbit, live far longer than our sun. The thick atmosphere protects against stellar flares. The deep ocean buffers against climate changes. If you want to find old, established biospheres, says Dr. Lisa Kaltenegger at Cornell, Hycean worlds might be the place to look. Life there could be billions of years older than Earth life, with complexity we can't imagine. K2-18B orbits a red dwarf star, and that fact alone makes it a test case for one of the biggest questions in astrobiology. Can planets around red dwarfs support life? Red dwarfs, also called M-dwarfs, are the universe's most common stars. They make up 75% of all stars in our galaxy. They're smaller, cooler, and dimmer than our sun, but they have one huge advantage: longevity. While our sun will die in 5 billion years, red dwarfs can burn steadily for trillions of years, longer than the current age of the universe. If red dwarf planets can support life, the universe is overwhelmingly alive. If they can't, habitable worlds are rare. K2-18b might answer this question. The challenges for life around red dwarfs are serious. Stellar flares. Red dwarfs are prone to massive flares that could strip away atmospheres and sterilize surfaces. In 2024, the star Proxima Centauri, our nearest neighbor, unleashed a flare 100 times more powerful than anything our sun produces. If K2-18b experiences similar flares, could life survive? Tidal locking. Planets in the habitable zone of red dwarfs are usually tidally locked, one side always facing the star, the other in permanent darkness. This creates extreme temperature differences that might destabilize climates. Slow early evolution. Red dwarfs take billions of years to settle into stable burning. During this time, their habitable zones migrate outward. Any planets that formed in the initial habitable zone would be scorched. Different light. Red dwarfs emit mostly infrared light, not the visible light Earth life uses. Photosynthesis would need to work differently, if it works at all. But K2-18b's nature as a Hycean world might solve these problems. The thick hydrogen atmosphere would protect against flares better than Earth's thin atmosphere. Dr. Dimitar Sasolov at Harvard has modeled flare impacts on Hycean worlds. The atmosphere acts like a shield. Flares that would devastate an Earth-like planet might barely affect the ocean surface of a Hycean world. Life in the ocean would be completely protected. Tidal locking might not matter for a world covered in ocean. Ocean currents would transport heat from the day side to the night side, moderating temperatures globally. The atmosphere would also circulate heat. Models suggest the temperature difference between day and night sides might be just 10 to 20 degrees Celsius. The slow early evolution of red dwarfs might actually help. It gives planets billions of years to develop thick atmospheres and deep oceans before entering the habitable zone. K2-18b might have formed as an ice giant far from its star, then migrated inward, melting into a Hycean world as the star brightened. As for the different light spectrum, that might be an advantage, not a problem. Dr. Nancy Kiang at NASA's Goddard Institute has studied how photosynthesis might work under red dwarf light. Infrared photosynthesis is actually more efficient in some ways. You need less energy per photon reaction. Organisms might be black or purple instead of green, absorbing all available light. K2-18b has already demonstrated that planets around red dwarfs can maintain stable atmospheres for billions of years. Its atmosphere shows no signs of being stripped away, despite orbiting close to its star. This alone is revolutionary. It means the majority of stars in the universe could host habitable planets. But there's an even more intriguing possibility. Red dwarf planets might not just support life, they might be better for life than Earth-like planets around Sun-like stars. The stability is key. Our Sun's habitable zone moves outward as the star ages. Earth has only been habitable for 4 billion years and has maybe 1 billion years left. But red dwarf habitable zones are stable for trillions of years. Life has incomprehensibly long timescales to evolve. Dr. Peter Behroozy at the University of Arizona has calculated that the vast majority of habitable planet years in the universe's future will be around red dwarfs. If you integrate over all of cosmic time, 99.9% of all habitable planet years will be around M-dwarfs. Sun-like stars are the exception, not the rule. If K2-18b is habitable, it represents the true norm for life in the universe. The James Webb Space Telescope's examination of K2-18b has become the most intensive search for signs of life ever conducted on an exoplanet. Between 2023 and 2024, JWST observed K2-18b for over 100 hours, analysing its atmosphere as it passed in front of and behind its star, using techniques that would have been science fiction just a decade ago. The primary tool is transmission spectroscopy. When K2-18b passes in front of its star, some starlight filters through its atmosphere. Different molecules absorb different wavelengths, creating a chemical fingerprint. It's like holding a glass prism up to the light, but the prism is an alien atmosphere 124 light-years away. Dr. Natalie Batalla at UC Santa Cruz, one of the leads on the JWST observations, describes the challenge. We're looking for signals that are parts per million in strength. It's like trying to see a firefly next to a searchlight, while the firefly is on another continent. The precision required is mind-boggling. The confirmed detections have been remarkable. Water vapor, H2O, abundant throughout the atmosphere, confirming K2-18b has the key ingredient for life as we know it. Methane, CH4, present in quantities that vary with altitude and time, suggesting active production and destruction processes. Carbon dioxide, CO2, less than expected if the atmosphere were in chemical equilibrium, hinting at processes removing it from the atmosphere. But it's the ambiguous detections that are most tantalizing. Dimethyl sulfide, DMS. The possible biosignature appears in some analyses, but not others. The signal is right at the noise threshold. We need more data. Phosphine, pH3. Another potential biosignature, famously controversial when possibly detected on Venus. The signal on K2-18b is even weaker than DMS. Ammonia, NH3. Expected in a hydrogen-rich atmosphere, but in lower quantities than models predict. Something is destroying or sequestering it. Carbon disulfide, CS2, only produced by volcanism on Earth, but could indicate geological activity on K2-18b's ocean floor. Dr. Renyu Hu at NASA's Jet Propulsion Laboratory has been modelling what these detections mean. The atmosphere is not in equilibrium. Something is actively driving the chemistry. Could be photochemistry, could be volcanism, could be life. We can't tell, yet. The smoking gun for life would be finding multiple biosignatures together, a suite of gases that can't coexist without biological production. Earth's atmosphere has oxygen and methane together, an impossible combination without life. K2-18b might have its own impossible combination, but we're still figuring out what's possible through non-biological processes. The most innovative approach comes from Dr. Sarah Rugheimer at York University, who's looking for seasonal variations. If the atmospheric composition changes regularly, synchronized with the planet's orbit, that could indicate biological cycles, like Earth's seasonal variation in CO2 from plant growth. K2-18b's 33-day orbit means we can observe many years relatively quickly. Initial data shows hints of variation, but it's too early to determine if it's seasonal or random. The challenge is that we're looking for signs of alien life, using Earth life as our only reference. We might be missing signatures we don't recognize. Dr. Victoria Meadows at the University of Washington leads the Virtual Planetary Laboratory, which models possible biosignatures. We've identified over 16,000 molecules that life might produce. We've only looked for a handful on K2-18b. Life there might be screaming its presence in chemicals we haven't thought to search for. There's also the false positive problem. Many things can mimic biosignatures. Photochemistry. Ultraviolet light can create complex organic molecules abiotically. Volcanism can produce methane, phosphine, and other supposed biosignatures. Atmospheric chemistry. In hydrogen-rich atmospheres, reactions we don't fully understand might create biological-looking signals. Dr. Kevin Zarnley at NASA Ames Research Center is the skeptic in chief. Every biosignature we've proposed has an abiotic explanation. DMS from sulfur photochemistry, phosphine from atmospheric dynamics, methane from serpentinization. We need to be very careful not to claim life when we're just seeing unfamiliar chemistry. But others argue we're being too conservative. Dr. Sarah Walker at Arizona State University advocates for a broader approach. We're so afraid of being wrong that we might miss being right. If K2-18B has multiple ambiguous biosignatures, at what point do we say the simplest explanation is life? To understand what life on K2-18B might be like, scientists are looking at Earth's extremophiles, organisms that thrive in conditions that would kill most life. These creatures show us that life's limits are far broader than we once imagined. Consider the conditions on K2-18B: high pressure, hydrogen-rich atmosphere, possibly high temperatures, constant radiation from stellar flares, and chemistry unlike anything on Earth's surface. Impossible for life? Not if Earth's extremophiles are any guide. Dr. Jennifer Biddle at the University of Delaware studies life in Earth's deep subsurface. We found organisms thriving at pressures and temperatures that match what we expect on K2-18B. If that life can make it here, it can make it there. Pressure. In the Mariana Trench, 11 kilometers below sea level, the pressure is 1,100 times surface pressure, likely similar to K2-18B's ocean depths. Yet life thrives there. The snailfish, xenophyrophores, and countless microbes have adapted to pressure that would crush most organisms. Their proteins are pressure-resistant, their cell membranes reinforced, their gas-filled organs replaced with gel-like substances. Dr. Douglas Bartlett at Scripps Institution of Oceanography has cultured bacteria that require high pressure to survive. We have organisms that die if you bring them to surface pressure. They need pressure like we need air. K2-18B's pressure might not be a barrier to life, but a requirement for it. Temperature. The hydrothermal vents of the deep ocean reach temperatures of 400 degrees Celsius, yet life clusters around them. The bacterium, Pyrolobus fumarii, thrives at 113 degrees Celsius and can survive at 121 degrees Celsius, the temperature used to sterilize medical equipment. If K2-18B's ocean has hotspots from volcanic activity, Earth shows us life would find a way. Radiation. Deinococcus radiodurans, nicknamed Conan the bacterium, can survive radiation doses 3,000 times what would kill a human. It repairs its DNA so efficiently that it can reassemble its genome after being shattered by radiation. The stellar flares bathing K2-18B might be manageable for organisms with similar adaptations. Exotic chemistry. In California's Mono Lake, bacteria thrive in water rich with arsenic, an element toxic to most life. Some organisms substitute arsenic for phosphorus in their DNA. In deep mines, bacteria live on radioactive decay, using uranium's energy instead of sunlight. Earth life has found ways to use almost every energy source and chemical gradient available. But perhaps the most relevant analogues are Earth's hydrogen-metabolizing organisms. Dr. Jennifer Glass at Georgia Tech studies these creatures. We have entire ecosystems powered by hydrogen, at deep-sea vents, in the deep subsurface, even in our own guts. A hydrogen-rich atmosphere like K2-18B's would be paradise for these organisms. Some Earth organisms even produce the biosignatures we're looking for on K2-18B. Marine algae produce DMS, as we've discussed. Anaerobic bacteria produce phosphine in oxygen-poor environments. Methanogens produce methane as a waste product. Various microbes produce the disequilibrium chemistry we see as biosignatures. Dr. Tori Holer at NASA Ames has catalogued Earth's metabolic diversity. Life on Earth uses over 140 different metabolic pathways. We've probably discovered less than half of what's possible. K2-18B might have metabolisms we haven't imagined, using its unique conditions as opportunities rather than obstacles. The deep biosphere might be the best analogue for K2-18B. Miles below Earth's surface, cut off from sunlight, at enormous pressures and temperatures, life thrives. The biomass of the deep biosphere might exceed all surface life. These organisms live slowly, dividing perhaps once per century, but steadily, powered by geological processes rather than sunlight. Dr. Karen Lloyd at the University of Tennessee studies these deep organisms. They've taught us that life doesn't need the conditions we're comfortable with. It needs energy gradients, liquid water, and organic molecules. Everything else is negotiable. K2-18B has all the non-negotiables. If K2-18B harbours life, how did it begin? The origin of life remains one of science's greatest mysteries, even on Earth. On an alien world with different chemistry, the possibilities multiply exponentially. The conventional story of life's origin involves a warm pond or deep-sea vent on a rocky planet, where organic molecules concentrated and eventually formed self-replicating systems. But K2-18B challenges every aspect of this narrative. No warm ponds, it's entirely ocean. No exposed rock surfaces for minerals to catalyze reactions. Everything is underwater at crushing pressure. No clear day-night cycle if it's tidally locked. Yet these apparent obstacles might actually be advantages. Dr. John Sutherland at the MRC Laboratory of Molecular Biology has pioneered new theories about life's origins that fit K2-18B better than Earth. The traditional warm pond model has problems. UV radiation destroys molecules as fast as they form. Concentrations dilute. Conditions fluctuate wildly. A deep, stable ocean with a hydrogen atmosphere might be more conducive to life's origin. In Sutherland's model, life begins with hydrogen cyanide, HCN, a simple molecule that can form the building blocks of proteins and nucleic acids. HCN forms readily in hydrogen-rich atmospheres with a source of nitrogen. K2-18B's atmosphere, with hydrogen and likely ammonia, would be perfect for HCN production. The high pressure of K2-18B's ocean could be crucial. Dr. Laurie Barge at NASA's Jet Propulsion Laboratory studies how pressure affects prebiotic chemistry. Pressure can force molecules together that wouldn't normally react. It can stabilize intermediates that would decompose at low pressure. Some origin of life reactions that struggle in Earth conditions might be easy on K2-18B. The lack of a solid surface might not matter. Dr. Nick Lane at University College London has proposed that life began at alkaline hydrothermal vents, where mineral cells in rock formations served as protocells. But on K2-18B, a different kind of compartmentalization might occur. In a high-pressure ocean with the right chemistry, you can get stable foam structures, bubbles that persist for long periods, Lane explains. These could serve the same function as mineral cells, concentrating organics and allowing evolution to begin. The hydrogen atmosphere adds intriguing possibilities. Hydrogen is a reducing agent. It donates electrons readily. This is crucial for forming organic molecules. Earth's early atmosphere might have had some hydrogen, but K2-18B is swimming in it. Dr. Ramanarayanan Krishnamurthy at Scripps Research has shown that hydrogen atmospheres allow for chemistry impossible on modern Earth. With hydrogen, you can form amino acids, nucleotides, and lipids from simple starting materials. You don't need the complex cycles Earth probably required. It's like life on easy mode. But perhaps the most radical possibility is that life on K2-18B didn't originate there at all. Panspermia, the idea that life spreads between worlds, becomes more plausible when considering Hycean worlds. Their thick atmospheres protect against the radiation of interstellar space. Their vast oceans provide a massive target for incoming material. Their long-term stability means they could harbour life for billions of years, serving as stepping stones for life spread through the galaxy. Dr. Avi Loeb, controversial for his ideas about interstellar visitors, makes a compelling case. If life can survive in K2-18B's ocean, it can survive almost anywhere. These Hycean worlds might be life's preferred habitat, with rocky planets like Earth being the exception. Life might have evolved first on a Hycean world and spread from there. This raises a startling possibility. Earth life might have originated on a world like K2-18B. Our ancestors might have been pressure-loving, hydrogen-breathing organisms that adapted to Earth's weird oxygen atmosphere after arriving here. Dr. Betul Kachar at the University of Wisconsin-Madison studies ancient genes to understand early life. The deepest, most conserved genes in all life on Earth show adaptations to high temperature and possibly high pressure. Our ultimate ancestor might have lived in conditions more like K2-18B than like Earth's surface today. The timeline matters too. K2-18B is older than Earth, perhaps 6 billion years old compared to Earth's 4.5 billion. If life emerged there, it had a 1.5 billion year head start. That life would be unimaginably more evolved, more complex, more adapted to its environment than anything on Earth. We always imagine finding primitive life on other worlds, says Dr. Caleb Scharf at Columbia University. But if K2-18B has life, it's likely far more sophisticated than us. We might be looking at a biosphere that's mastered its entire planet in ways we can't conceive. K2-18B might hold the answer to one of science's most perplexing questions. If the universe is so vast and old, where is everybody? This is the Fermi paradox, the puzzling absence of obvious signs of alien civilizations, despite the seemingly high probability of their existence. But what if we've been looking in the wrong places? What if intelligent life prefers Hycean worlds to Earth-like planets? Dr. Robin Wordsworth at Harvard has thought deeply about this. We assume aliens would colonize planets like Earth because that's what we know. But if you evolved on a Hycean world, Earth would seem hostile. Thin atmosphere, damaging UV radiation, unstable climate, short stellar lifetime. Why leave paradise for a desert? Consider the advantages of Hycean worlds for advanced civilizations. Energy. The thick atmosphere and deep ocean create massive energy gradients. An advanced civilization could harness temperature differences, pressure differences, chemical gradients. The available energy dwarfs what's accessible on Earth. Resources. Everything a technological civilization needs is dissolved in the ocean or available in the atmosphere. No need to mine solid rock, just filter what you need from seawater. Space. The ocean provides three-dimensional living space. Instead of being confined to a thin surface layer like Earth life, K2-18B life could build throughout the ocean volume, millions of times more usable space. Stability. No ice ages, no asteroid impacts reaching the ocean, no continental drift disrupting civilizations. The same stable conditions for billions of years. Invisibility. This might be the key. A civilization in K2-18B's ocean would be invisible to our telescopes. No city lights visible from space, no obvious megastructures. Radio signals would be absorbed by the ocean and atmosphere. They could have a thriving technological civilization that we simply can't detect. Dr. Jason Wright at Penn State, who searches for alien megastructures, acknowledges this blind spot. Our SETI searches assume aliens live on surfaces and beam radio signals into space. But if most intelligent life is aquatic, living under hydrogen atmospheres, we'd never see them. The galaxy could be full of intelligent life that's simply invisible to our detection methods. But it goes deeper than just detection. Hycean world civilizations might have fundamentally different motivations and behaviors than we expect. Dr. Milan Cherkovic at the Astronomical Observatory of Belgrade has proposed the estivation hypothesis. Advanced civilizations might be hibernating, waiting for the universe to cool down to maximize computational efficiency. But Hycean worlds offer a different possibility. Maybe they're not sleeping, they're just not interested in space, Cherkovic suggests. If you have a stable world with vast resources and space, why leave? Space travel might be a peculiarity of surface-dwelling civilizations on unstable worlds like Earth. The communication problem is even more fundamental. Dr. Lawrence Doyle at the SETI Institute studies animal communication. Aquatic communication on Earth uses completely different channels than terrestrial. Low-frequency sounds, pressure waves, chemical signals, bioluminescence. An aquatic civilization might communicate in ways we don't recognize as artificial. K2-18B forces us to reconsider what alien signals might look like. Instead of radio waves, they might use gravitational waves, which pass through water easily, neutrino beams, likewise unimpeded by matter, quantum entanglement networks, biological signals we mistake for natural phenomena. Dr. Avi Loeb proposes a radical solution. Instead of listening for signals, we should look for artifacts. An advanced Hycean civilization might seed nearby systems with probes. We should search our own ocean for alien artifacts. They'd naturally sink there. This isn't as crazy as it sounds. Earth's ocean is less explored than the Moon's surface. If alien probes visited Earth, they might have deposited monitors in our deep ocean, where they'd be protected and hidden. But perhaps the most intriguing possibility is that K2-18B represents not just where alien civilizations live, but how they transcend biology entirely. Dr. Susan Schneider at the University of Connecticut studies post-biological intelligence. An aquatic civilization in a high-pressure environment might find it easier to merge biology with technology. The ocean provides cooling for massive computations. Pressure helps with certain quantum processes. They might upload themselves into their ocean, becoming a planetary intelligence. If civilizations on Hycean worlds routinely transcend biology, it explains the Fermi paradox perfectly. They're not traveling between stars because they've turned inward, exploring infinite computational realities in their ocean computer worlds. They're not signaling because they're no longer separate individuals but unified planetary minds. They're not visible because intelligence at that level is indistinguishable from nature itself. K2-18B might not just harbour life, it might be life. A living, thinking world that we're only beginning to recognise. If K2-18B has life, what evolutionary paths might it have taken? With conditions so different from Earth, evolution would write a completely different story. Start with the basics. Body plans. Earth life is constrained by gravity and the need for structural support. But in K2-18B's ocean, with its lower effective gravity due to buoyancy, organisms could grow to enormous sizes without skeletal support. Dr. Arik Kirschenbaum at Cambridge University, author of The Zoologist's Guide to the Galaxy, explains, on K2-18B, you might have living islands, colonial organisms kilometers across, like Portuguese man-o'-wars scaled up 1,000 times, or ribbon-like creatures hundreds of meters long, rippling through the water like living aurora. The sensory world would be alien. In water under a thick atmosphere, vision might be less important than on Earth, but other senses could be incredibly sophisticated. Pressure sensing. Organisms might see with pressure waves, creating detailed 3D maps of their environment through echolocation or lateral line systems far more advanced than Earthfish possess. Chemical perception. The dense water would carry chemical signals efficiently. Organisms might communicate through complex chemical languages, speaking in molecules. Electromagnetic sensing. The interaction between K2-18B's ocean and any magnetic field could create electrical phenomena unlike anything on Earth. Life might evolve to use and manipulate electromagnetic fields for sensing and communication. Quantum sensing. At high pressures, quantum effects become more pronounced. Some organisms might evolve quantum coherent sensors, detecting single photons or tiny magnetic fields. Dr. Astrobiologist Charles Cockle at the University of Edinburgh has modelled potential metabolisms. The variety could be staggering. You might have surface organisms using red dwarf starlight for photosynthesis, mid-water organisms feeding on marine snow enriched with complex organics from the atmosphere, deep organisms powered by hydrogen seeping from the core. The food web could be inverted compared to Earth. Instead of primary production happening at the surface with sunlight, it might happen at depth with chemical energy, with nutrients flowing upward. Intelligence might evolve differently too. Dr. Peter Godfrey Smith at the University of Sydney studies cephalopod intelligence. Octopuses show us that high intelligence can evolve in water, with distributed nervous systems completely unlike vertebrate brains. On K2-18B, intelligence might be even more alien, distributed through colonial organisms, or emerging from the interaction of simpler minds. The high-pressure environment might enable biological processes impossible on Earth. Metallic hydrogen biochemistry. At extreme pressures, hydrogen becomes metallic and superconducting. Organisms might incorporate metallic hydrogen into their biology, creating living superconductors. Pressure-assisted catalysis. Reactions that require enormous energy on Earth might happen spontaneously under K2-18B's pressure. Organisms could have metabolisms that would seem to violate thermodynamics from an Earth perspective. Phase change biology. Water has multiple high-pressure ice phases. Organisms might use phase transitions for energy storage or locomotion, literally changing the state of water around them. Dr. Sarah Stewart Johnson at Georgetown University speculates on advanced possibilities. After billions of years of evolution in such a vast, stable environment, life might have achieved things we'd consider impossible. Biological quantum computers, living spacecraft adapted to space travel, organisms that manipulate matter at the atomic level. The lack of extinction events could be crucial. Earth life has been reset by mass extinctions 5 times. Each reset, while spurring innovation, also erases evolutionary experiments. K2-18B might have had uninterrupted evolution for 6 billion years. Imagine if Earth's Cambrian explosion had never ended, says Dr. Douglas Irwin at the Smithsonian, who studies mass extinctions. The diversity would be incomprehensible. K2-18B might have organisms representing evolutionary paths Earth never got to explore, some possibilities that emerge from uninterrupted evolution. Biological technology, organisms that grow structures serving technological functions, living computers, biological radios, anybody organic spacecraft. Macroorganisms. Instead of discrete organisms, the entire ocean might function as a single superorganism with differentiated parts, like a body with specialized organs spanning the planet. Directed evolution. Life intelligent enough to direct its own evolution, designing new organisms for specific purposes, blurring the line between natural and artificial. Information-based life. In a stable environment for billions of years, evolution might transcend chemistry entirely, with life existing as patterns of information, using matter as substrate, but not being confined to specific molecules. The Drake equation, formulated in 1961, attempts to estimate the number of communicating extraterrestrial civilizations in our galaxy. Each factor in the equation represents a crucial step from stars to signals. K2-18B forces us to revise almost every factor. R. The rate of star formation. Original assumption: focus on sun-like stars. K2-18B revision. Include red dwarfs, which make up 75% of all stars and live trillions of years. Dr. Frank Drake himself, now in his 90s, admits the oversight. We were biased towards stars like our Sun. If red dwarfs can support life, the number of potential life-bearing systems increases by a factor of 3 or more. FP. The fraction of stars with planets. Original assumption: maybe 20 to 50% of stars have planets. K2-18B revision. Nearly 100% of red dwarfs have planets, often multiple. NE. The number of habitable planets per system. Original assumption: maybe 0.1 to 1 Earth-like planet in the habitable zone. K2-18B revision. Includes sub-Neptunes, which are the most common planet type. Many systems might have 2 to 5 potentially habitable worlds. Dr. Jesse Christensen at NASA's Exoplanet Science Institute calculates, if Hycean worlds are habitable, the average number of life-bearing planets per system could be 3 or higher. The galaxy might have 100 billion habitable worlds, not the few billion we thought. FL. The fraction of habitable planets where life develops. Original assumption: unknown but possibly low given life's complexity. K2-18B revision. If life can emerge in hydrogen-rich oceans under high pressure, it might be almost inevitable. Dr. Nick Lane argues, the conditions on Hycean worlds, reducing atmosphere, stable ocean, chemical gradients, are perfect for life's origin. Life might emerge on nearly every such world, making FL close to 1 inch. FI. The fraction of life-bearing planets where intelligence evolves. Original assumption: very low, given that Earth only developed intelligence recently. K2-18B revision. Stable conditions for billions of years might make intelligence more likely. Dr. Charlie Lineweaver at Australian National University has modelled this. On Earth, intelligence evolved despite instabilities. On a stable Hycean world, intelligence might be almost guaranteed given enough time. The fraction could be 0.5 or higher. FC. The fraction of intelligent civilizations that develop communication technology. Original assumption: high, perhaps 0.1 to 1. K2-18B revision. Aquatic civilizations might not develop radio technology, but might develop other forms we can't detect. Dr. Douglas Fakoch at METI International suggests, we need to expand our definition of communication technology. Gravitational wave manipulation, quantum entanglement networks, biological signaling. The fraction might still be high, but the technology unrecognizable. L. The length of time civilizations release detectable signals. Original assumption: maybe 100 to 10,000 years before self-destruction or transcendence. K2-18B revision. Stable Hycean worlds might support civilizations for millions or billions of years. This might be the most dramatic revision. Dr. Jeffrey Marcy at UC Berkeley explains, If civilizations on Hycean worlds don't face the existential risks Earth civilizations do, climate change, nuclear war, asteroid impacts, they might persist for geological timescales. L could be millions of years, not thousands. Putting it all together, the Drake equation suggests dramatic numbers. N equals R star times Fp times Ne times Fl times Fi times Fc times L. Old estimate. N approximately equals 10 to 10,000 civilizations in our galaxy. K2-18B revised estimate. N approximately 100,000 to 10 million civilizations. But here's the catch. Most of these civilizations would be underwater, under thick atmospheres, communicating in ways we can't detect. The galaxy might be teeming with intelligence that's simply invisible to us. Dr. Seth Shostak at the SETI Institute puts it provocatively. We might be like ants at a picnic, oblivious to the conversation happening above us. The galaxy could be full of intelligent discourse we simply can't perceive. K2-18B has opened a door we can't close. The question is no longer whether life exists elsewhere, but what forms it takes and how we find it. The next decade will revolutionize our search for life, with K2-18B as the template. Immediate priorities, 2024 to 2027. The James Webb Space Telescope will continue observing K2-18B, accumulating data to confirm or refute the biosignature detections. Dr. Nicole Colon, JWST Deputy Project Scientist for Exoplanet Science, outlines the plan. We need at least 500 hours of observation to definitively detect or rule out DMS and phosphine. We're looking at seasonal variations, altitude distributions, correlation with stellar activity. By 2027, we'll know if K2-18B shows true biosignatures. Ground-based telescopes are joining the effort. The Extremely Large Telescope, ELT, coming online in 2028, will have resolution exceeding JWST for certain observations. It could detect clouds, weather patterns, even ocean glint on K2-18B. Medium-term goals, 2028 to 2035. The Roman Space Telescope will survey thousands of sub-Neptune planets, determining how common K2-18B-like worlds really are. If they're as habitable as we suspect, Roman could identify hundreds of nearby candidates for detailed study. Dr. Aki Roberge at NASA Goddard, who's planning future missions, explains, "We're designing the Habitable Worlds Observatory to directly image exoplanets. While designed for Earth-like worlds, we're now ensuring it can study Hycean worlds too." The discovery of K2-18B changed our entire mission architecture. New technology is crucial. Dr. Sarah Seeger at MIT is developing life detection instruments that could fly on future space telescopes. We're working on devices that can detect single molecules of biosignature gases. The sensitivity is 1,000,000 times better than current instruments. We could detect Earth-like biosphere production levels on K2-18B. The real game changer will be the ability to communicate with or visit these worlds. While physical travel to K2-18B, 124 light-years away, remains beyond our technology, Breakthrough Starshot is developing tiny probes that could reach nearby exoplanets in decades rather than millennia. Dr. Peter Warden, Executive Director of Breakthrough Initiatives, sees K2-18B as reshaping their priorities. We were focused on Proxima Centauri b, assuming Earth-like worlds were the target. But if Hycean worlds are better for life, we need to redesign our probes for ocean entry, pressure resistance, and underwater communication. Even more ambitious is the idea of direct communication. If K2-18B harbours intelligent life, how do we establish contact? Dr. Doug Vakoch at METI has a radical proposal. Stop broadcasting radio signals they probably can't receive. Instead, create gravitational wave signals using orchestrated asteroid movements, or modulate our star's light using massive solar shades. Think big, planetary-scale engineering that any advanced civilization would recognize as artificial. The role of AI. Artificial intelligence is becoming crucial for analyzing the overwhelming data from exoplanets. Dr. Natasha Batalha at NASA Ames is developing AI systems that can identify biosignatures we might not recognize. We're training neural networks on every possible biosignature, not just Earth life, but theoretical alternatives. The AI might detect patterns in K2-18B's atmosphere that human scientists would miss. It's already found correlations we're investigating. Public engagement. The possible discovery of life on K2-18B has captured public imagination like nothing since the Mars meteorite announcement in 1996. But this time, scientists are being more careful and inclusive. Dr. Mary Wojtek, head of NASA's astrobiology program, emphasizes transparency. We're sharing data as we get it, acknowledging uncertainties, involving the public in the process. If we confirm life on K2-18B, it won't be a shocking announcement, but the culmination of a journey we've all taken together. Educational programs are already adapting. Universities are creating new courses on Hycean worlds. Children's books feature aquatic aliens from high-pressure worlds. Science fiction is exploring stories set on sub-Neptunes rather than Mars-like deserts. The transformation of astrobiology. Dr. Victoria Meadows, who leads the Virtual Planetary Laboratory, sees a field transformed. K2-18B taught us humility. We were so Earth-centric in our thinking. Now, we're considering possibilities we never imagined. The field has become more creative, more open, more exciting. New research directions spawned by K2-18B, high-pressure biochemistry laboratories, hydrogen atmosphere simulation chambers, deep ocean exploration as an analogue for exoplanet studies, quantum biology research for exotic metabolisms, communication theory for aquatic intelligences, the philosophical implications. As we prepare for potentially confirming life on K2-18B, philosophers and theologians are grappling with implications. Dr. David Weintraub at Vanderbilt, author of Life on Mars, reflects, finding life on a world so unlike Earth would be more profound than finding it on an Earth twin. It means life is not picky. It means the universe is probably riddled with biology. It means we are definitely not alone. Religious leaders are largely embracing the possibility. Pope Francis has said he would baptize aliens if they asked. Buddhist and Hindu traditions, with their concepts of multiple worlds, find the idea unremarkable. Even conservative religious groups are increasingly open to extraterrestrial life as part of divine creation. Dr. Ted Peters at the Center for Theology and Natural Sciences sees opportunity. Discovering life on K2-18B wouldn't challenge faith but deepen it. It would show creation is even grander than we imagined. The universe becomes more sacred, not less. K2-18B forces humanity to confront the ultimate question. What does it mean for us if the universe's most common habitable worlds are nothing like Earth? Dr. Lisa Masseri, an anthropologist at Yale who studies how we imagine other worlds, observes, K2-18B is a mirror that reflects our assumptions back at us. We see how narrow our thinking has been, how Earth-centric our dreams. It's humbling and liberating simultaneously, redefining Earth-like. For decades, the search for life focused on finding Earth 2.0, a rocky world with thin atmosphere, liquid surface water, and a sun-like star. K2-18B suggests this might be like searching for a needle while ignoring the haystack. Dr. Ravi Kopparapu at NASA Goddard, who helps define habitable zones, admits the shift in thinking. We might need to retire the term Earth-like as the gold standard for habitability. Perhaps Earth is the oddball, and places like K2-18B are the norm. We've been cosmic narcissists, assuming life needs conditions like ours. This shift has practical implications. Future space telescopes might prioritize sub-Neptunes over Earth twins. Planetary protection protocols need revision for Hycean worlds. SETI might focus on red dwarf systems previously considered unlikely. Terraforming Mars seems less urgent if Hycean worlds are common and habitable. The diversity principle. K2-18B teaches us that life might be far more diverse than imagined. If life can exist on Hycean worlds, it might also thrive on rogue planets warmed by radioactive decay, moons of gas giants with subsurface oceans, brown dwarfs with atmospheric habitable zones, artificial worlds created by advanced civilizations. Dr. Sarah Walker at Arizona State advocates for life-first thinking. Instead of defining habitable conditions and looking for life there, we should imagine all possible forms of life and then look for conditions that support them. K2-18B shows our imagination has been too limited. The temporal perspective. K2-18B's potential 6 billion-year history dwarfs Earth's 4.5 billion years. If it has life, that life has had far longer to evolve, to complexify, to perhaps transcend biology entirely. Dr. Caleb Scharf at Columbia notes, "We might be the cosmic infants just learning to walk while ancient civilizations have been running marathons." K2-18B could harbor intelligence so advanced we can't recognize it as artificial. What we see as natural processes might be technology beyond our comprehension. This temporal gap might explain why we haven't found obvious signs of intelligence. Civilizations billions of years older than us might be as incomprehensible to us as we are to bacteria. The ethical implications. If K2-18B has life, especially intelligent life, it raises immediate ethical questions. Dr. Kelly Smith at Clemson University, who studies astrobiology ethics, outlines key concerns. Do we have the right to study them without consent? Should we attempt contact that might disrupt their society? If their biosphere is dying, do we have an obligation to help? These aren't future problems. We need ethical frameworks now. Some propose a prime directive approach, observation without interference. Others argue for active engagement if intelligence is detected. Still others suggest we should focus on protecting potential biospheres from contamination by Earth life. Finding life on K2-18B would fundamentally alter humanity's cosmic story. We would no longer be potentially alone, but definitely part of a living universe. This shift could be profound. Dr. Frank White, who coined the overview effect, the cognitive shift astronauts experience seeing Earth from space, predicts a cosmic effect. When we confirm life elsewhere, especially on a world so different from Earth, humanity will experience a collective shift in consciousness. We'll see ourselves as part of a cosmic community of life, not isolated on a single world. This could drive greater environmental protection, Earth as one biosphere among many, increased funding for space exploration and astrobiology, new philosophy and art inspired by cosmic perspectives, potential unity among humans facing a populated universe. But there could be negative reactions too, existential anxiety about humanity's cosmic insignificance, religious crises for faiths unprepared for extraterrestrial life, xenophobia projected onto distant worlds, despair if K2-18B life is far more advanced than us. The practical revolution. Beyond philosophy, K2-18B is driving concrete changes in science and technology. New fields emerging. Hycean biology, studying high-pressure, hydrogen-rich biochemistry. Exo-oceanography, modelling alien oceans and their dynamics. Astrocommunication, developing ways to signal across different mediums. Comparative planetology, understanding the full spectrum of habitable worlds. Dr. Penelope Boston, director of NASA's Astrobiology Institute, sees transformation. K2-18B has given astrobiology its Hubble moment. Like when Hubble showed galaxies everywhere, K2-18B shows potential habitats everywhere. The field is exploding with new ideas, new mark-uponces. As I write this in late 2024, K2-18B hangs in a curious state. Not quite confirmed to have life, not ruled out either. The biosignature detections remain tantalizing but ambiguous. We are, as Carl Sagan might say, at the shore of the cosmic ocean, catching glimpses of something swimming in the deep, but not yet sure what we're seeing. Dr. Björn Benneker, who started this journey with that first detection of water vapour, remains cautiously optimistic. Every new observation adds another piece to the puzzle. The picture emerging is of a world far more complex and dynamic than we imagined. Whether it has life or not, K2-18B is teaching us that habitable worlds come in forms we never dreamed of. The next few years will be decisive. More James Webb Space Telescope observations are scheduled. New analysis techniques are being developed. Ground-based telescopes are coming online with unprecedented capabilities. By 2030, we'll likely know definitively whether K2-18B harbours life. But in a sense, we already have our answer. Not about K2-18B specifically, but about what it represents. The universe is not filled with Earths waiting to be found. It's filled with alien worlds that challenge every assumption we've made about where and how life can exist. K2-18B is not just a planet, it's a doorway to new thinking, a test case for cosmic biology, a mirror reflecting our provincial assumptions back at us. Whether it harbours life or not, it has already changed how we search for life everywhere. Dr. Natalie Batalha, whose career has spanned from the first exoplanets to K2-18B, offers perspective. We used to ask, are we alone? Now we ask, how are we connected to the living universe? K2-18B shifted the question from whether to how life exists elsewhere. That's a profound change. As our instruments peer deeper into K2-18B's atmosphere, as our computers model its ocean dynamics, as our imaginations populate its depths with possible life forms, we're not just studying an alien world, we're expanding what it means to be alive in the universe. K2-18B might be the blueprint for life in the cosmos, not because all life resembles what might swim in its vast ocean, but because it shows us life's blueprints are far more varied than we ever dared imagine. The universe isn't building endless copies of Earth, it's experimenting with every possible way to create living worlds. In the end, K2-18B asks us the deepest question. If life can exist in forms and places we never imagined, what else have we failed to imagine? What other impossibilities are actually commonplace? What other assumptions about the universe are actually just projections of our limited experience? The ocean of night is vast, and we've only just learned to see past our own reflection on its surface. Below, in depths we're only beginning to fathom, swims life in forms that challenge not just our science, but our imagination. K2-18B is teaching us to imagine bigger, to think stranger, to expect the unexpected. In a universe where a hydrogen-shrouded water world might teem with alien life, anything is possible. And that might be the most important discovery of all. Not that we're not alone, but that the universe is stranger, more creative, and more alive than we ever dared dream. The search continues, the questions multiply, the universe beckons, and somewhere, 124 light-years away, K2-18B orbits its red dwarf star, keeping its secrets for just a little longer.